Hello students, I am Ms. Pooja Kalandi, Assistant Professor from ISMR MCA. Welcome you back to this video lecture on LPT. So today we'll be covering a very important concept of duality. So let's see what is basically dual. Duality concept deals that a normal solution or a normal function which is given in LPT is considered as primal solution, and then we calculate a dual from this primal solution. So let's see what is the theory behind this. Okay. So see, if you can see here, the given is a maximization problem where the objective function z is equal to c1 x1 plus c2 x2. Now you know that in maximization problem there should be always less than equal to sign here, okay? And you know in minimization it should be always greater than equal. Okay, so in this case you can see here now it is given as a11. So these are the constraints. Okay, so a11 into x1 plus a12 into x2 plus a1n into xn less than equal to b1. Again a21 x1 plus a22 x2 plus dot 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 a2n xn less than equal to b2. So this will continue till am1 x1 plus am2 x2 plus dot 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 amn xn less than equal to bm x1 x2 greater than equal to 0. So normally you can just understand that this is a normal maximization problem where these variables are being considered. So this is the objective function and these are the constraints. Now how will be the dual of this function? So basically you have to calculate the transpose of a matrix. So you know how to calculate a transpose of matrix. In transposition of matrix, the rows are interchanged to columns. So you will convert rows into columns. So if you observe this, how will this look as? So in this case, what will happen in the dual concept is that these values will get changed. So this B1, B2 will be replacing the values of C here, and the x will be replaced by y, and instead of these a11 a12 we will be having the transpose. So these rows will be interchanged by column values. Okay, so now let's see how the dual looks like. So as I told you, these b values will come in the objective function. Now the objective function from maximization will go to minimization. I've taken another variable w, which will be b1 y1. As I told you, x will be replaced by y, b1 y1 plus b2 y2 plus so on. And now if you see here, instead of this is 1112, it has become 1121, means these was the row. Now the values are taken according to the column. So if you see here, it is going to be a11 y1, x is being replaced by y, plus a21 y2 plus dot 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 am1 ym. The sign has also changed, greater than equal to c1 as it is a minimization problem, and this c is nothing but the values which are present in the coefficients of the objective function. So now you can see here it has become a12 y1 plus a22 y2 plus dot 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 am2 ym greater than equal to c2. Then a1n y1 plus a2n y2 plus okay dot 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 amn ym greater than equal to cn y1 y2 greater than equal to 0. Now this was the theory. Just you have to remember that the objective functions coefficients c are being replaced by the coefficients of the or the values at the last values which are b. Then the x1 x values are replaced by y, and instead of a1112 rows will be interchanged by columns, and this c values coefficients will be going at the replacing this b values. Okay, and the signs will be changing. A maximization problem will get converted into minimization problem. So instead of seeing this theory, now we'll see a problem on this case. Okay, so as you can see here, it is given, write the dual of the given LPP. It is minimization problem. Z is equal to 3x1 minus 2x2 minus 4x3. So I've just written here the coefficients 3 minus 2 minus 4. Okay. Now in this case, it is a minimization. So these are all greater than equal to constraints. In maximization, you know, it is less than equal to constraint. Now the subjective constraints, there are how many constraints here? In total, there are how many constraints? Okay, so there are 1, 2, 3, 4, and 5 constraints. So subject to 3x1 plus 5x2 plus 4x3 greater than equal to 7, 6x1 plus x2 plus 3x3 greater than equal to 4, 7x1 minus 2x2 minus x3 less than equal to 10, x1 minus 2x2 plus 5x3 greater than equal to 3, and 4x1 plus 7x2 minus 2x3 greater than equal to 2, x1, x2, x3 greater than equal to 0, this should be x3. Okay, now see in this case, since it is a minimization, you should have all less than equal to, greater than equal to. So this is greater than equal to, this is also greater than equal to, this is not greater than equal to, and these two are also greater than equal to. So now we have to convert this into greater than equal to. For that you have to multiply it by -1. So this equation will become, or this constant will become as minus 7x1 minus will become plus 2x2 minus will become plus x3 greater than equal to plus 10 will become minus 10. Now if you can see here, I have written this total subject constraints in the form of the matrix equation. So this is 3 5 4 6 1 3 minus 7 minus 2, this should be minus 2. Okay, sorry, minus 7 2 1 1 minus 2 5, and the last one 4 7 minus 2. Okay, so this, if you see it is a transpose, what will you do? You will write this columns as rows. So this will become 3 6 minus 7 1 4, 5 1 2 minus 2 7, and 4 3 1 5 minus 2. This is just a shortcut how to remember this. So now in the same manner we will be converting this given LPP in the dual form. So as I told you that these last values will be the objective function coefficient. So this becomes as W, a maximization problem, 7y1 plus 4y2 minus 10y2 plus 3y4 plus 2y5. So if you see, these values have been replaced as the coefficient of the objective function, these last values. Okay, so this we have got the objective function. Now x is being replaced by y. Now you can check out these values. See here, I've taken the transpose, 3y1 plus 6y2 minus 7y3 plus 1y4 plus 4y5 is less than equal to, now you'll have the values from this part, that is the 3. So 3 for the first equation, 5 for the second equation, and 4 for the third equation or the constraint. So rows, the columns have interchanged to rows. Now the second row will be what? 5y1 plus 1y2 plus 2y3 minus 2y4 plus, okay, this should be 7y5. Okay, so 7y5 is less than equal to minus 2, because here it is, okay, just a minute, what I've said, okay, less than equal to, this should be, okay, this part it should be minus 2, as this is the objective function here. Okay, then the third column will be 4y1 plus 3y2 plus 1y3 plus 5y4 minus 2y5 less than equal to minus 4. This minus 4 will come from the objective function part, that is the minus 4. So 3 minus 2 minus 4. So if you see here, these values, I repeat again, these values have formed, these coefficients have formed the objective function coefficients, 7, 4, minus 10, 3, 2. These columns have interchanged to rows. Okay, so you can see these column values have been interchanged to row values, and the last coefficients here we are getting it from the objective function, 3 minus 2 minus 4, and the minimization problem has got converted to the maximization problem with the change in the sign. Okay, so this is the way to find a dual. I have taken one more problem. This is a simple problem. Okay, you can see here, right dual of the given LPP. This is a maximization problem. Now you know that this maximization problem will get converted into a minimization problem. This is less than equal to, so this is 492 coefficients. Now this is less than equal to, so we will be converting this into equality. So for this reason, the W will become this two parts. So that is 7y1 plus 5y2. So I have written here the transpose, 2 3 2 2 3 2 3 minus 2 4. So the transpose will become 2 3 3 minus 2 2 4, interchanging rows to column. I will write the equation in the same way, 2y1 plus 3y2, 3y1 minus 2y2, 2y1 plus 4y2, and these values are nothing but the values of the objective coefficients of the objective function, that is here 4, 9 and 2. So I hope you are clear with the duality concept, that is how to write a dual from maximization problem to minimization problem, minimization problem to maximization problem. Try to practice more problems on this, because this is going to form the basis for the dual simplex method. So just give a go through to this and try to solve more problems in order to practice this. This is a very easy concept. So I thank you for watching this video. Thank you.